A very warm good evening to one and all present over here. Today the Leadership Lecture Series invites you for the talk on Femto-to-Macro scale engineering applications covering commercial research educational opportunities via nuclear-centric technologies. Today we have Professor Rusi Taleyarkhan over here. Professor Rusi Taleyarkhan received his BTech in Mechanical Engineering in 1977 from IIT-Madras, followed with a Master's in Business Administration and PhD in Nuclear Engineering by 1982 from Rensselaer's Polytechnic Institute, USA. He has since worked as senior engineer with Westinghouse Electric Corporation through 1988, after which he spent over 17 years where he was program director and distinguished R&D engineer at US DOE's Oak Ridge National Laboratory, conducting and leading energy, defense and energy-related projects, both classified and unclassified. He joined Purdue University in 2003 as Professor of Nuclear Engineering, where he teaches and conducts multi-disciplinary research. He has published over 175 articles in the archival literature and has received over 25 invention awards besides numerous industry and government recognitions. During 2004, his work was declared by Science News as Top 10 Science Discoveries and by the Energy Times as World's Top 6 Must-Do Research Projects for the 21st century. Professor Taleyarkhan has consulted extensively for various national and international bodies. He is a Fellow of the American Nuclear Society and the Honorary Fellow of the Russian Academy of Sciences, member of ASME, TSS and a lot. He was also the past editor of the Nuclear Safety Journal. We are very pleased to have you over here, sir.
Hey, good afternoon, folks. Can you hear me at the back? Can you understand my Tamil accent for all these years? Okay, so that was the introduction. So without further ado, let me move forward. I'd like to say I feel like I'm home again. And some of the most memorable years of my life, and I'm sure many of your lives, are going to be at this particular institution, this great institution of ours. A special thanks to IIT-M's Professor Nagarajan, Latha, and a whole host of other people that have been so kind to invite me over here. I'm currently working at this place called Purdue University. Not everybody calls it Purdue University. Many of them call them the Boilermakers, and there's a history behind that, which I won't get into today. But that's the university that was established in 1874 with just about 39 students. Currently, we have about 75,000 students. One thing that Purdue University takes a lot of pride in is to say that we've got probably one of the world's largest living alumni. The word living is important because these are the guys that donate to the university. And I guess that's important for alumni associations and for so on. Our budget is about $2.3 billion, regularly ranked, at least in engineering, as the top 10 United States universities. Faculty staff roughly equal in terms of numbers and physical plant. And our president currently is Mr. Mitch Daniels. He was the previous chief minister of the state, what in the US is called governor. A real dynamo of an individual who is very interested in a collaborative relationship between IIT-Madras and Purdue University, which is one of the reasons why I'm over here. School of Nuclear Engineering, which is my home school over there. I work in the College of Engineering. We really do not have too many stovepipes, so to speak. We collaborate extensively. But some of the things that I would like to sort of point out over here is that this particular school that was established over 30 to 40 years ago during the Manhattan Project years currently graduates over 10% of all the nuclear engineering graduates in the United States. They go across a whole range of disciplines, not just nuclear power, a whole bunch of additional areas. We've got a nuclear reactor on campus, accelerators, isotopes, and so on. There's the famous blue glow that you see out of a nuclear reactor. There's nothing fancy. It is just something what we call Cherenkov radiation. That is, in one case, one easy way of representing this. These are particles, fundamental particles that are moving faster than the speed of light in that medium that produces this unique blue glow. We use it for quite a few experiments, research, as well as for teaching purposes. Nuclear technology, I'd like to at least give a brief flavor to what this particular footprint encompasses. But how did it all start as an evolution? If you go back, there was nothing called nuclear in the past. Even 500 BC, the word atom was coined as constituting the smallest indivisible object, and all atoms were supposed to remain stable so far. For about 2,000 years, nothing happened to this concept except in the 1890s and 1800s and so on, people started finding that, well, there's something called radioactivity. Not atoms were all stable. That rocked the boat like crazy. Yeah? The concept of the nucleus and nucleons, that is the constituents of the nucleus of an atom, came about. And one fundamental particle after another started getting discovered and understood. These are all in the femtometer scales. Yeah? 1927 was when nuclear fusion, accelerator-based nuclear fusion, was postulated and discovered, well before fission was discovered. And I guess the realization that, well, if you can make this particular process happen in a controlled fashion, the energy output could be millions of times greater than what you could get out of chemical combustion. Huge potential, huge potential. In the 1930s, for the first time in history, people recognized that, well, just because nature produces or has in place certain isotopes that are radioactive, that are not stable, you can now produce artificial radioactivity. Something that allows you now to make elements and isotopes that never existed before. Well, previously about 200 elements and isotopes existed, some of them stable, some of them unstable. Now the field mushroomed like crazy. Today you have over 2,000 of these isotopes. Virtually 90% of them, 80% of them man-made. Things that never happened before or that never existed before. Controlled fission came about. We knew now how to create new elements, isotopes at will. Well, in the 1940s, as you know, the Manhattan Project produced something called a WMD, weapon for mass destruction. It was deployed over Hiroshima and Nagasaki. You can be on either side of the fence. But it demonstrated the unlimited energy generation potential as well as the potential energy destruction potential at the same time. So the same knife that you use to butter your bread could be used to, I guess, slit somebody's throat. Yeah? Recognitions that radiation can also alter or mutate cells, change the functionality of the cells themselves. In an uncontrolled fashion, it causes cancer and death. As we all know, I guess, lots of radiation can cause that to happen. The cell basically stops to sort of grow in a controlled fashion, and I guess that results in death. But in a controlled fashion, it can give you all kinds of desired properties that have been deployed over the past 40, 50 years, right after artificial radioactivity was discovered, to change the way life is today. Damping events have been TMI2, Chernobyl, and Fukushima for nuclear energy. But at present, there's been a huge technological expansion in virtually all walks of life. And I'm going to share just a few moments with you to give you an idea of what those expansions have covered. In the US alone, based upon a 1995 study and extrapolated somewhat, the footprint is over $500 billion per year of cross-cutting applications. Cross-cutting applications across a whole swath of everyday items that we take for granted. Here are some of them. Electricity. We all think about nuclear energy as being associated with just nuclear power and so on. Well, in countries like France, 80% of the country's electricity is generated from electricity, 15% worldwide. In the US, it's about 20%, much, much lower in India, but hopefully on the rise up. You've got food safety. You can delay ripening of fruits and products. You can defeat pathogens. Science research, we use that for curing AIDS, for understanding cancer, for magnetism, for dating. Now, this is not like the human dating variety. It's to date objects. How far back did something happen? Yeah? Geologically and so on. Industry. I was in Saudi Arabia not too long ago, and I recognized that, well, they're one of the largest users of radioisotopes. They use them for oil well logging and for control of different systems. We use them in emergency signs you see at airports every once in a while. There's no electrical wires going to those lights. How are those lights lighting up all the time? Those are tritium-based lights. Yeah, matter? Use them for security, for smoke detectors worldwide. Tiny quantities of americium-241 keep those things going. Yeah? Space mission. You could not go to Mars and back without killing yourself. You could have a 90% fuel reduction, for example. Radioisotope power is already used for all kinds of space missions that go for for decades at a time. Yeah? You don't have access to solar power or conventional batteries and so on. There's consumer products. Every time a lady puts up lipstick on their face, guess how that lipstick was sanitized? Yeah? If you ever see how lipstick is made, it's like a sausage factory. Yeah? All kinds of crap that goes inside over here. You use radiation to sort of sterilize all those bacteria. Polymerization is used all throughout. If you ever wonder how your pants become wrinkle-free, how you do sort of cross-linking and so on, all of that is done through polymerization. When I was working at Westinghouse, one of the chief scientists over there was Harry Ferrari. He was not from the rich Ferrari family of Italy, but he was the inventor of radiation-induced hardening of tennis cut strings, and he had the first patent on that. He could afford a couple of Ferraris of his own afterwards, yeah, as a consequence. There's all kinds of stories in this way. Agriculture is immensely influenced. For example, insect control. There were certain insects that were destroying entire food crops in the US and worldwide. We found a way called the sterile insect technique that sterilizes insects into mass populations, and you can then basically make them go away and preserve your agriculture. Seed preserves, for example, plant metabolism. Medicine is a huge user of nuclear technologies, PET scans, SPECT scans, sterilization, treatments, even hydrogen production today, and so on. And so the bottom line is, you ask the question not where nuclear technology is being used, or show me, rather than asking the question, show me a place where nuclear technology is not used. Think about it. It's not just nuclear power. Yeah? This particular component that we usually consider as being nuclear engineering, is only 5–10% of the total footprint across the globe. Yeah? In the US is about 10%, 15%. Everything else is something other than just nuclear power. So something, at least a very brief primer on energy from taming of the atom. What's the real firepower that you get from nuclear technology? The nucleus has forces that bind the nucleons together. If you compare that to the force of gravity, as you see yourself jumping and coming down, this is like 10 to the 40 times greater. It's as close to infinity as you're going to get in a human's lifetime. Yeah? Not too many forces that compare to these levels. The energy generation potential comes from essentially two types. One of them is fission. Fission you can consider to be like divorce. Yeah? Things breaking apart, families breaking apart over here. There's breakup of heavy nuclei like uranium that releases about 200 million electron volts per fission. Now, never mind what a million electron volt or even an electron volt means. Fusion produces in a marriage type format. This is a very short marriage, by the way. It lasts in the femtoseconds. Once the fusion takes place, it breaks apart anyway. Yeah? But this is a mating of light nuclei that produce about 20 MeV per fusion. But on a mass basis, fusion is 10 times greater than that for fission. Overall, the combustion energies only give you about 10 EV per combustion of atoms. So the energy generation potential, relatively speaking, is about 10 million times greater. Yeah? Vast reserves of fuel, especially for fusion, and that's what keeps the fusion machine going for decades and decades and decades. It's always 40 years away. Yeah? But on the flip side, there's radiation to be contended with from a safety viewpoint. There's waste issues, there's proliferation issues, there's storage issues, and so on, which have enormous scientific challenges and opportunities at the same time. Just to say, here's what one nuclear plant would equate to in terms of railroad cars of coal per year. 1,000 megawatt plant. Yeah? No greenhouse gases. I teach a course on various aspects of nuclear technology applications. One of them is on radiography. Yeah? Whenever we think about conventional radiography, people think about X-rays being used. But there's an entire field that people are taking opportunities on based upon neutrons. I'll just give you a few examples. How would you like to know the blossoming of a flower? How do flowers blossom over time? It's very difficult to use X-ray techniques to get any idea. With neutron techniques, you can actually see the petals growing one by one, all across, the outside to the inside. Glucose uptake in plants. In real time, you can see that, and you can try to now figure out how to apply your phosphorus-based fertilizers and so on, in what proportions, in what position, in what point in time, and so on too. Yeah? looking inside a 1-inch thick, 2.5 centimeter thick lead box for something concealed inside. If you use X-ray techniques, all your X-rays are basically gobbled up by the lead, yeah? But you could see that little gun sitting inside, yeah? There's something called coloring gemstones with radiation sources. There are E-beams, gamma rays, reactor neutrons that are utilized. Here's an example of topaz that is mined from the ground. Chalky looking stuff has almost no gemstone value. You can turn that into a light blue and it jumps in value by a factor of 100. You can get a deep blue color and now it becomes gemstone quality. Yeah? Something that you throw away to something that allows you to make money right underneath diamonds. Yeah? What's the value proposition? Here's an example of a blue diamond that was purchased for about $48 million by a Hong Kong billionaire for his daughter. Not too many fathers can afford that. Yeah? But what if you had radiation technology at your disposal? A 12-carat white stone at a Geneva auction sold for $48 million. Yeah? The nuclear techniques provide unparalleled deep colors, unlike any other technique. Virtually all of the world's 1 carat and below diamonds that are colored deep blue come from nuclear technology applications. So imagine the value proposition. Something called a Cape diamond that you almost throw away or use for machine tools and so on can be turned into gemstone quality. And now of course, somebody with money was going to pay you for it. Yeah? Okay. We always hear about long life batteries. They last for weeks and maybe months and so on. How about something like lifelong batteries? What is life? Lifelong means, well, different things to different people. But at least for an ordinary human being, you think about 40 years, 50 years. You can easily make that happen through beta voltaics. You want a lifelong battery for space applications, let's say about 40 years. You can make that happen too. You want something that lasts you for a few nanoseconds, even that's a possibility. Yeah? All right, so think outside the box, so to speak. Yeah? Lots of opportunities over here. These are called beta voltaics. So I'd like to now introduce some of the I guess, current RPT group, that's my initials, group thrust areas that at least my group at IIT, that I'm looking for IIT-M Purdue collaborations, yeah? And so-called opportunities on a faculty to faculty type level. I do not speak for the whole university at the present time. Yeah? Ongoing primary areas in my group. First of all, we are addressing the combating of nuclear terrorism. It is considered to be in the top 3 of the world's major 21st century grand challenges to overcome. There's no point having all the money in the world or all the energy in the world if somebody is going to blow you up. Yeah? Just not there anymore. Alleviating leading lung cancer causes from radon gas in homes and so on, in buildings. We're coming up with novel green polylactic acid radiation-tailored polymers that affect a $200 million market in the US alone. Yeah? And of course, cavitation control, which is fundamental and has multiple disciplinary impacts. Other potential cross-cutting opportunities, safety of LNG industries from RPTs, that stands for rapid phase transitions, aluminum metal casting, where people lose lives every other week from explosion events. How do you prevent those explosion events? You transfer technology from the nuclear technology arena to that. Metallurgy, supercooling, and superplasticity. How do you produce nanoscale powders cheaply enough? And fundamental heat transfer enhancements via radiation-induced surface activation. These are some of the other areas that we're working on too. And of course, coming up with lifelong batteries. That's still in the research phase, but the top 4 are the ones we are already commercializing. And I'm looking for opportunities to work with IIT. Super compression, well, one of the techniques we've developed that was previously deployed for thermonuclear fusion induction has now been proven capable of producing diamond states from ordinary graphite powders. Yeah? All right? You need high pressure and high temperatures. Okay, here's a listing of the top few grand challenge for the 21st century. First of all, on everybody's mind is, if I have limitless energy, most of the world's problems go away. If I have enough energy that's cheap enough, I can desalinate water, I can take care of water problems. If I have enough energy, people don't have to fight wars over oil and so on and so forth. Well, making energy from fusion. is I guess, people's minds. Of course, making solar energy economical. But solar energy is also nuclear fusion, by the way. Yeah? All right? So if you can make this economical, well, it's a paradigm shift. But number 3, very close to that, is to prevent nuclear terrorism. We live in a world where the number of these special nuclear materials has proliferated quite a bit all across the globe. The US is responsible, India is responsible, Pakistan is responsible, and so are countries like North Korea. All it takes is a little grapefruit size material, and you lose the whole of Chennai or Chicago or New York. Yeah? God forbid. We must not allow that to happen. It's a global issue. Anyway, so it's a tremendously challenging technical problem as well. And so that's what we are addressing over here. It is one of the top 10 challenges. A Hiroshima type device can be equated to about 17,000 tons of TNT. 1 kilogram of TNT produces about 3 to 4 megajoules of energy. You can imagine all of that energy being released within a microsecond. It's like about 100 million cars on the road moving at 100 kilometers per hour, all slamming into something or somebody at the same time. 100 million of them. Yeah? You all know what this mushroom cloud stands for. Yeah? But most of these issues for combating nuclear terrorism, you say, can be overcome with timely detection and interdiction. What the world really needs are transformational sensors. The sensors people use in the field today are based upon nuclear power technology of 40, 50 years. Big, clumsy, expensive, yeah? And not very efficient. We need to sort of come up with something which are efficient to the tune of about 95 to 100% compared to 1 to 20%. Something that can go in the range of about a few dollars to about tens of thousands of dollars rather than tens of millions of dollars. Yeah? And with directionality and robust and intuitive and so on. I'll give you some examples over here. One of the interdisciplinary solutions from Purdue research group is what we call the tension metastable fluid mechanical material sensor architecture. What it does is to combine mechanical engineering, materials engineering, chemical engineering, electrical, and of course nuclear physics and engineering, together with all these aspects of optics, acoustics, and so on, with policy and global security with commercial payoffs immediately available. Before 9/11 took place in the United States, there was no Department of Homeland Security. Right after that, it's become the second largest department in the United States government today, about $70 billion a year, second only to the Department of Defense. So what is metastability? A brief primer. What we do is to sort of place fluids, liquids, just like ordinary coffee or water, into states of tension metastability. So that is, you're trying to stretch the molecules. You might say, how are you going to stretch fluid? You try to sort of stretch anything, it just rinse off. But indeed, you can do that. This is a typical PV diagram that you should recognize, P versus V. Here it is, this thing is moving on its own. Yeah? I'm not pressing anything. There you go. Is there something going on that's moving the thing by itself? Or should I look at this? I'm not doing anything. All right, let me go back. I'll do it the old-fashioned way. Yeah? All right, so here's your PV diagram, and here's your liquid phase, here's all your vapor phase, and in between is 2 phase. And conventionally, you come down an isotherm and you start boiling up until everything becomes vapor. You then become an alpha equals 1, that is void fraction equals 1. But if you're careful on how you treat your fluids without allowing cavitation to take place, you can bring down the tension, the pressure of that fluid at the same temperature, well down to its so-called tension limit, and a bit further on, of course, you can also superheat to its superheat limit. At the superheat limit, the liquid automatically will boil on its own. Homogeneous nucleation can take place. That's a phenomena which won the Nobel Prize for Dave Glasser in 1960s. That became the so-called bubble chamber. And you can actually tension fluids to their spinoidal limits, and we've taken water all the way down to minus 20,000 psi or minus 1,700 bars, atmospheres and so on. At that point, you just breathe on it and the thing will explode. Yeah? So here's an example of how the nuclear process works. Nuclear scale process works. These are fundamental particles these have the wavelengths of the femtometer range. Neutrons, fast neutrons or alpha decays and so on. They strike the heart of a nucleus, the neutron scatters away, the nuclei, these are ionized particles, take that energy and they deposit their energy inside the fluid over a given spatial dimension of a few nanometers, and they can form, they can seed little bubbles. Something is not right. Okay, all right. So once the critical radius to the first order 2 sigma, 2 times the surface free energy is overcome, divided by the differences in the pressures on the outside and inside is overcome, the bubbles can grow to macroscopic scales. You can physically see and hear them now. Physical manifestation of something on the femtometer scale within nanoseconds to the microscale. Yeah? That turns into a detector system of sorts. Yeah? So how does it compare against the current gold standard? These are called the helium-3 detectors. You look at efficiencies, and I'll just let it march forward. Yeah? On-off times, these take minutes. These can be done to microseconds. You've got to remain blind to the background gammas and so on. Oh, in this case, no. In that case, yes. Can you do things like directionality and multiplicity? The answer is no. And ultimately, the bottom line figure in somebody's brain is going to be how much is it going to cost. These guys cost tens of thousands of dollars. We could do this thing within hundreds of dollars or thereabouts. So that's the business proposition, which allows you to attract commercialization funds from private investor groups and so on. Most academics don't like to think about money, but believe me, in today's world, you've got to do that. Yeah? You've got to become entrepreneurs yourself. And here's one simple method with which you can create these tension metastable states. You just take a little piece of glassware, diamond shaped, you fill it with some fluid up to this point. Up to this point, and you rotate it about its axis. The molecules over here race outwards in this direction. Molecules over here race outwards in that direction. It becomes a self-stabilizing mechanism. There's always a lot of rotational flows in the central region, but beyond a certain rotational speed and arm separation, this one, you can get through the Bernoulli's law principle a unique value for the pressure state over here. You don't need any instrument to tell you that. All you need to know is the rotational speed and this particular separation and the density of the fluid. And if you can avoid spurious nucleation, you've got yourself a system as simple as this that you can put together for tens of dollars or a few hundred rupees, compared to something that would cost you tens of thousands of dollars to produce and a PhD degree in physics to operate. Yeah? So something as simple as that. So even fundamental particles can be detected and studied, and a typical high energy neutron, at least from fission and so on, is going to be in the MeV range. That translates into about 1/10 of a picojoule of energy. You know how much energy it takes to boil water? It's a few megajoules per kilogram, all right? Over here, something with 0.1 picojoules directly targeted onto the nucleus of an atom inside a tension fluid can cause that thing to boil in front of your eyes at room temperature. That's the power of this process. Yeah, Mara? The possibilities could be endless. We are also considering using it for looking at dark matter and so on. Here's an example. For a neutron of a mass, something like 10 to the minus 27 kilograms, of the size of about 10 to the minus 15 meters, that is in the femto scale, can locally boil water and so on at room temperature. It allows you to physically see and hear the fundamental particle effects, so to speak. You can see and hear radiation in a way, rather than relying on electronic equipment. So how could that be done? Here's a little example of a unit that's currently being marketed and possibly being considered for deployment at the Tokyo Olympics. Yeah, Mara? What you're seeing over here is that apparatus which is rotating, and a nuclear source is going to come inside, and it's going to punch a bubble inside there. Yeah? For some reason, this is not cooperating, guys. So keep your eye on this central region over there. You will see the moment a neutron comes inside, it will blow a cavity in this region. Did you see that flash? The flash takes place, and in slow motion, you can see that gas cavity that has evolved going out. Now you can see a larger view. And these are little sensors on the side that we place inside that can see these flashes within nanoseconds, and you can detect and record and so on. So a system as simple as this would be completely blind to photons and betas and so on, but would be super sensitive only to the particles of interest that come from special nuclear materials, like neutrons and alphas and so on. So it's a marriage of nuclear physics with conventional mechanics, mechanical engineering, chemical engineering, and so on. Yeah? And of course, material science over here. Another system is the acoustic-based system. In this case, what you do is to put together a cavity, an acoustic cavity with a top and bottom reflector, and drive it with piezoelectrics from the side. And those things operate in the tens of kilohertz type range, and you set up a standing wave. And the standing wave allows you to go plus or minus in pressure inside this particular cavity. And when it turns negative, it becomes sensitive. If it turns positive, it's no longer sensitive to anything. Yeah? So it becomes a continuous system. Here's an example. If you are sitting next to it, I don't know if there's sound over here, but this is something like about 100 bubble bursts per second taking place. That was a plutonium source coming inside on the side. Yeah? And you can record the position and the number of these events, and you can record them and find out what the intensity of the source was and where that source is coming from. Yeah? Something about radon. I don't know how many people are aware that this is one of the world's leading causes for lung cancer. Especially in the US, there's something like 20,000 deaths, over 21,000 deaths from lung cancer alone caused by radon. And exposure to radon, as we say, well, causes those many deaths, is the number one leading cause. Allowable EPA limits are something like picocuries per liter. What does that translate into? In terms of concentration per unit volume, you have something like 10 to the minus 17 grams per liter. Extraordinarily small quantities, which makes it very difficult to detect by conventional sensors. They take hours and days and weeks, and they cost something like tens of thousands of dollars. Not the charcoal canisters, they cost only about tens of bucks, but then those are collectors, those are not detectors. You're going to send them off someplace else to detect. Yeah? Big difference. And so present day systems, they cost 5,000 to tens of thousands. They're simply impractical to use in homes and offices like smoke detectors. Imagine if you could come up with something to the $100 or less range. Every home at least in the United States, opens up as a potential market. So about 200 million homes at least. Yeah? And it is a death caused not just in the US. Every life matters all across the globe. It is available to the masses. This could become a potentially huge impact. Yeah? We're already doing that today, and we're looking for collaborations to make this system even more user-friendly and I guess overcome some of the technical challenges, engineering challenges that remain. Yeah? Something about optics. The same system that detects neutrons and so on could also be utilized for looking at optics, laser optics, for example. There's a laser beam coming in, a very, very weak laser beam, UV laser beam with something like 10 to the 13 photons of I guess, a few EV per photon, and you can detect the bubble track, yeah? And look at the intensities and characterize where somebody is shining a laser at you for pointing. The nuclear navy loves this kind of thing because if somebody is trying to sort of track your motion using laser optics, then if you know where that optics is coming from, you can know which way to sort of direct your firepower, yeah? To sort of return the favor, so to speak. Cavitation control in systems, they're caused by particulates, motes, non-condensable gases, imperfect wetting, and so on. And the stimuli that can cause these effects to take place can be mechanical, which is in the few centimeters wavelength, laser optics in the micron range, gamma photons in the picometer ranges, and also fast neutrons and so on, dark matter in the femtometer range that can cause cavitation to take place. Enormous fundamental science and engineering implications. Fluid propulsion systems, for example, to prevent choking in fuel lines. Every time somebody wants to press a gas pedal and try to get a big thrust from an F-16 fighter jet, if the line gets choked because of cavitation, you just can't get any more fuel. If you can prevent cavitation on that front, when the pressure drops to vacuum conditions and below, you've got the firepower available to you to sort of move even faster G levels. Yeah? Moving masses, propellers, if you can prevent cavitation on the tips of propellers, not only do you prevent erosion of the propeller blades, but also make the submarine silent. Yeah? The number one item for undersea warfare. Multi-component fluid mixture control for chemical process industries, acoustically agitated systems, mixing control, medical applications for lithotripsy and so on. That is a technique currently employed for destroying kidney stones and so on. Yeah? Nanoscale formation, static fluid medium, and so on. If you're interested, come see me for any one of these topics, but these are all opportunities we are applying this technology into. Yeah? We've already done this to successfully allow water, organic fluids like ethanol, and even jet fuel like dodecane to be brought down in pressure to about minus 10 bars, that is minus 100 psi below perfect vacuum, and not allow cavitation to take place. Ordinary cavitation will take place the moment you get below a few psi under 1 bar of pressure. And we also find that while this technique, these types of techniques allow the fluid to almost behave like human beings, to retain a sense of memory that at one point they were treated to that particular treatment, and it retains that memory all throughout. Yeah? PLA tech is another area that we are working on now. This is an eco-friendly polylactic acid based hot melt adhesive sealant technology for autos, for engineered woods applications, and at the same time being completely free of formaldehydes and VOCs. There's a huge potential market for this one. This particular technology we've developed for the creation of adhesives for the auto industry and elsewhere, which can be tailored for properties using radiation technologies, has been proven to be almost universal in this application. You can join steel to steel, steel to aluminum, which is something very difficult to do in terms of welding, hardboards, plywoods, cardboards, bricks. You can even join brick to brick. You don't need cement now, for example. Yeah? Concrete to concrete, even marble to marble, fabric to glass to glass, ceramics. You can join plates and so on. If you break a plate, put it together. Virtually all metals tested, including Teflon, which is one of the most difficult things to join. Yeah? Very smooth stuff. The strength properties can be varied at will depending upon what technique you deploy. We use different techniques and got up to 6,000 psi. So that's something like 6 times 6. So about 42 megapascals, yeah, over there. And unclamped conventional epoxies or like super glues basically go only up to about 1,000 psi. Yeah. We've done plywood applications. You know how common plywood is. If you recognize how plywoods are actually made in industry with adhesives that use urea formaldehyde, you would understand the degree of toxicity involved. Yeah? Once you make it, this thing keeps on emanating urea formaldehyde into homes and offices and so on. And that's a current issue for which the EPA is now increasing its foothold on the standards. Yeah? So we've been able to come up with something that has met all the industry standards on that front. Several of these areas are currently being heading towards commercialization and have been commercialized. There are product brochures that we've developed for the acoustic-based sensing system that are utilized not just for detection but also for tracking special nuclear materials on fast-moving conveyor belts and so on, for imaging them, to seeing them in situ and so on, for use in reprocessing plants as well as in everyday home life, radon as well as PLA tech. And I'd like to sort of end this particular talk. I've got a few more slides that can talk about some of the other applications. We believe that there's a significant amount of potential. I met with several of the heads and faculty members in mechanical, metallurgical, chemical engineering. I think there's lots of potential for partnerships, especially with the students. Yes, Mara? I used to be one of you at one point in time. I'd love to be able to sort of get more of you. In my research group, I include students all the way from high school, all the way to the postdoc and visiting professor levels. I'd love to have as many from IIT-Madras as possible. And with that, I'd like to thank you folks for your attention. If there's any further questions, I'd be happy to answer them. Yeah? Thanks. Okay. Was it all clear or all unclear? You put it that way, yeah, Mark? Or just too boring enough to sort of sit through, yeah? Everything is fine, fair game. I might start asking questions to you folks. Yeah, go ahead. Yes, you had a question. Yeah.
So my question is that if you talk about creating low pressure is understandable, but the amount of energy that is deposited will actually tell you whether there is a nucleation or not, and you can see the reaction, right?
Right.
So for an unknown conveyor belt in a real time,
For an unknown
conveyor belt, like you talked about an application that you will scan materials. So in that case, how will you control the rotational rate, because it depends on the RPM of rotation to create the tension, or the amount of voltage you drive in for the piezoelectric result. So if you do not have it in a loop system, how will you control it in real time?
Okay, well, the answer to your question is, what are you trying to detect? We know that we have, if you're interested in special nuclear materials, they emit these so-called neutrons and particles in a fission spectrum, starting from very low energies all the way to about 12 MeV, so to speak. So if your interest is only in detection, you place your tension metastable state to the highest level possible. Now you can detect. Now if you want to know whether it's a cosmic or whether it is a special nuclear material, you just sweep the negative pressures and you get a spectrum out of it. And that spectrum is very unique from anything that I guess the cosmic showers can, I guess, produce. Yeah? So we do that in real time. Yeah.
Sir, whether you use only experiments or whether you use simulations also?
Oh yes, well that's a great question. We use both. I just did not have time to sort of talk about all the mathematical modeling and computational multi-physics that goes on behind the scenes. So we do multi-physics simulations, transient multi-physics simulations that combine fluid structure interactions, structural dynamics, fluid mechanics, CFD, and so on, together with nuclear particle transport. On an atom by atom basis. Yes, Mara? So we do that, and that's what allows you to sort of design systems and optimize them further. That's a separate field by itself, and I just did not have time to go over that. Yes, Mara? But if you're interested, just write to me, rusi@purdue.edu. I'll be happy to sort of send you as many papers as you might want to read. Yes, Mara?
Thank you, sir.
Sure thing. Who cracks knuckles? Your hand knuckles? You guys crack your knuckles every once in a while? You hear that click? What is that click? It's a cavitation bubble that you're creating. Don't do it too often, you'll get arthritis. Yeah? All right? Those imploding bubbles can do quite a bit of damage. And one of the experts in that kind of stuff, using acoustic induced cavitation is sitting right here, like Professor Nagarajan, from what I understand today. Yeah? All right, folks. Thanks a lot for your attention. Yes, Mara? Okay. All right.
Thank you for such a wonderful talk.
All right.
Now I invite Professor Nagarajan sir, Dean IITM, to give away the token of appreciation.
Oh, thank you so very much. All right. Thank you. All right. Thank you. Thanks, folks. Appreciate it. Come see me if you can. Yeah, Mark? Or if you folks are looking for summer research internships, write to us. Yeah, Mark? We're looking to sort of promote that kind of an exchange as well. I get a lot from IIT Kanpur and some of the other IITs. I want to get the ball rolling over here now. Yeah, Mark? All right. And I have a conflict of interest. I might choose this place more than others. Yeah, Mark? Okay. Declared conflict of interest. Okay. Thanks, folks.